Welcome to our Organic Chemistry 1 final exam review. Let's go ahead and dive into this, shall we? So what would you like, what's the first question or first topic that I can help y'all with? All questions are on the table. I'm ready for anything. Okay. There's a question about a reaction. It is a addition reaction of an alkene. I'll go ahead and draw the structure here so you can see. Basically, the substance looks like, here, let's see. I'll just do free draw. Looks like this. Alkene here, and then CH3 here. All right, and it says, what is the major product of the following reaction? So you got the CH3, and it's reacting with Br2, and in CCl4. Now the solvent is important in this case because if you had a different solvent on the bottom, like water, H2O, you'd get a completely different product. So in this case, does anybody know what type of reaction this would be? Okay. This is going to be an addition reaction. And specifically, this is a reaction that has a very specific stereochemical outcome. Okay? So when bromine reacts with this, what happens is you actually get something called a cyclic bromonium ion. So bromine kind of attacks this like this. I'm trying to see where I am. Okay, here we go. The electrons from the alkene attack the bromine kind of like this. So here's the bromine. 1, 2, 3. Here's my lone pairs of electrons. So you get this double bond grabs this bromine, and these electrons leave and go on the other bromine. But here's the weird part. These electrons here come back and form a bond here. So you end up with this weird looking cyclic bromonium ion. And basically, essentially you have a bromine here, and the bromine is bonded to both of these carbons as 2 lone pairs, and it's positively charged. Now, as you can imagine, it's not entirely that super stable. Now, here's the thing. The bromine can either add on top or add on bottom, and it can really do either. It's equally likely that it can add on top or bottom. But if it adds on top, what happens is you get this. You get a wedge here, and you get a wedge here. That, of course, means that the other one, the CH3, is in the back. Apologize for my terrible drawing. Okay. So now, what happens next will be, and this is a positive charge on the bromine. The other bromine that was let go, the Br, that was let go from 4, let's see. It has a negative charge. I'm thoroughly embarrassed at my drawing skills, but I do apologize. But essentially, this is going to come and attack. Now, which side is this bromine going to come and attack? Is it going to, for this particular one, is it going to attack on bottom or is it going to attack on top? What do you think? It's going to attack on bottom. And is it going to attack on the left side, or is it going to attack, is it going to attack the more highly substituted position or the less highly substituted position? Well, you might think it would be the less highly substituted position because it would be less sterically hindered. However, it turns out that it tends to target the more highly substituted position. At least if my reasoning, if I'm recalling correctly. And the reason is because the more highly substituted carbon, that this is not an even cyclic bromonium ion. Essentially, it's stretched. So you have the carbon, and you have the bromine. But let's say this one is attached to more things. Okay. This bond is, shall we say, longer and weaker than this bond, because you can have a partial positive on this carbon that's stabilized by the fact that it's tertiary, okay? And that's going to make this a better target for that negative bromine to come on in. So you end up with this coming in from the backside and kicking out the bromine and pushing it over. Now that does two interesting things, because it comes in from the bottom. It actually pops the CH3 up, but it also pops the other bromine up in the other position. And so what you end up with is something that looks like this. You end up with the bromine in the back, a CH3 that's wedged. Oh, I meant the C. The other C. And then you have this bromine wedge here. So this is going to be an anti-addition. The addition of the Br2 addition is going to be an anti-addition. The bromines are going to add on opposite sides. And of course there's lone pairs on those bromines. But I'm feeling lazy and I don't want to draw them out. So, okay, I guess I'll draw them out. But this is one of the products. But you also have to keep in mind that you're also going to get the enantiomer of this. So in other words, you could get, instead of this, you could also get its enantiomer, which would look like this. And essentially you'd have the dash bromine down here, and then you'd have the dash CH3 here, and then a wedge bromine here. Basically everything's kind of the opposite. And both of these would be equally likely. So both of these would be your major products. Does that make sense? Yeah, so if it was H2O instead of CCl4, that would give you the water adding to the more highly substituted position, because once again, like I mentioned before, the more highly substituted position is going to have this partial positive here. Now water tends to be a pretty weak nucleophile, so it's going to need a little help to kind of get in there. But here's the thing, the reason why water comes in and attacks it rather than the bromine, even though bromine's a better nucleophile, is because if water is the solvent, there's tons and tons and tons and tons of water molecules, plus This doesn't need a super great nucleophile because this cyclic bromonium ion is really unstable. It's really sterically, or it's very strained. It's very strained because you're forcing these bond angles to be about 60 degrees. And bromine's a good leaving group to begin with. So with that strain and with the 60 degrees, I mean, it's gonna break pretty easily. Oh, if it was water? Yeah, if it was, okay, so if it was water, let's see. If it was water, it would look like this. Let me do all the hard stuff. No, I'm just kidding. All right, let's see. So with water, this would end up adding H2O initially, but then one of the hydrogens would be abstracted and you'd end up with an alcohol. And then this, of course, would be your CH3. And then, of course, you'd have your wedge bromine. All right, yeah, and that's pretty much it. And of course, you'd also get the enantiomer to this, right? Everything would be switched around, which I'll just write as En because I don't feel like drawing another structure. But I can draw it if you want me to, but does that make sense? Okay, cool. Any other questions on either this or any other of the types of addition reactions? I want to pull up my SN1, SN2, E1, E2 elimination guide. Guide to all those substitution versus elimination flow chart. Guide to all those reactions. So, what else can I help you with? Don't be shy. I won't bite. At least if you're online. I make no promises to those here in person. And then the microphone goes off. No, just kidding. All right. So what can I help you with?
Are you able to, can you go over delta G and
Delta G?
And, yeah, so the free Gibbs energy and how temperature affects it along with delta H and delta S?
Okay, yeah. That's not typically an organic chemistry concept, but that was covered in your organic class?
Yes.
In what context?
One more time?
In what context?
So essentially, with the equation delta G equals delta H minus T delta S, I guess I'm just really trying to hone down like how temperature affects the sign of delta G.
Gotcha. Well, temperature, so if you're talking about this, temperature can affect the sign of delta G. It affects it depending on the sign of delta S. So and remember, delta S is the change in the disorder or change in the randomness in a reaction. So if the, here, reaction goes from a less ordered state to a more ordered state, then the delta S would be negative. So delta S is negative. That's when your products are more ordered than the reactant. You go towards a more ordered arrangement, less disordered. Okay? Now, if the delta S is positive, that means you've gone from a less or a more random state to from a less random state to a more random state. So it becomes more disordered. This would be, actually, you know, I'm going to use typing because that's easier. So this would be more, actually, let me size that. More disordered. So what does that mean? Well, basically, there's several ways to become more disordered or more random, but if you have more product molecules than reactant molecules, like if something splits apart, then that would be a positive delta S typically. If you have two or more molecules coming together to form one molecule, such as in a lot of the addition reactions, that ends up being going from less ordered to more ordered, so a positive delta G. Essentially what temperature will do is it will shift equilibrium in favor of more disorder, okay? So the temperature affects the disorder factor. And if the delta S is negative, that is not a spontaneous process generally. It does not usually spontaneously happen that things go from being less ordered to more ordered. In fact, in terms of the universe, it never happens. Not unless you have a sacrifice, somewhere else, okay? You can't make one thing more ordered without something else becoming more disordered. All right, so in light of that, a higher temperature, if the delta S is negative, a higher temperature will cause the delta G to be more positive because this is a negative term. And so if delta S is negative, you'll have a negative of a negative, and that'll be positive. Now, positive delta G means there's an increase in the available energy available to react. What that means is that somehow you put energy into the reactants to make a higher energy product. Once again, that's not something that can happen by itself because you can't create energy. Energy cannot be created or destroyed. The only thing that you can do is move energy from something else to it, and that requires a bit of work. That's not something that will happen on its own. So a higher temperature will cause a negative delta S to reaction to be less spontaneous or non-spontaneous, more non-spontaneous, more positive delta G. However, if the reaction goes from being a less ordered state to a more ordered state to a less ordered state, in other words, it becomes more disordered, delta S is positive, then a higher temperature will favor making the reaction spontaneous. I don't know if that answers your question.
Yeah, it clarifies it. Thank you.
Yeah, there's actually a good review of this on our website, but I'm going to go ahead and pull that particular review of that, and I'm going to paste it into the chat so that you can actually download it and have it available and look through it. It gives a little bit more detail than what I just went through, but I think that will be helpful to you. And for those of you who in here would like that, because you think it would be helpful or something, just let me know, and I will, in fact, go ahead and print that off for you, or if I have a copy of that, I'll go ahead and give it to you. All right, here, let me post that into the chat. Come on, chat. There we go. Bam. Chemical thermodynamics. There you go. All right. Next. Go ahead, Nick. Yeah, sure. What's the question? To predict the major and minor elimination products of the following reaction and consider stereochemistry in your answer. Okay, so this is an interesting question. Let's go ahead and take a look at it. I'll give this back to you in just a second. 1, 2, 3, 4, 5, 6, 7. Whoa, there we go. Okay. So then you have a wedge here, and you have a dash here. Cl. All right. And this is being eliminated via NaOH. Okay. So this is a really, really interesting question. Let me go ahead and give you this. This is not an easy question either. Basically, what you have to keep in mind is whenever you have an elimination reaction that proceeds via an E2 mechanism, and you can tell that this is going to be an E2 mechanism. Why? How do you know this is an E2 mechanism? What? No, they all have leaving groups. Oh, what'd you say? Not a bulky base. You can have a bulky base and still be E2. That's not the reason. Anybody know? How can you tell that this is going to be E2? What type of leaving group do you have? What type of carbon is it on? What'd you say? Secondary. It's a secondary leaving group, and what is it reacting with? A strong base. And E2 elimination will also always happen with a strong base and a moderately to significantly sterically hindered position. Okay, so like for example, secondary or tertiary, strong base and secondary or tertiary will always give you E2. Now the only way you can have E1 is if you have what? It has to be a weak base and a weak base, weak nucleophile. Exactly, and it helps if it's tertiary, but it can actually happen in secondary. It can actually happen in secondary. So here's the deal. Anytime you have E2 elimination, it always has to rip off a hydrogen that is anti-coplanar or anti-paraplanar to the leaving group. What does that mean? That's a fancy word. That means that the hydrogen has to be so I'm going to mark what's known as the alpha carbon. You should be familiar with this terminology. The alpha carbon is the carbon that has the leaving group. Okay? Or the alpha carbon can sometimes be referred to in terms of the center of reactivity, okay? So the alpha carbon is the carbon that has the leaving group in these types of reactions. Now, that means that any carbon that is next to it is going to be beta. So this is a beta carbon, and this is a beta carbon. I'm going to mark my beta carbon. I wrote beta in blue, but I'm going to, or maybe purple. I'm colorblind, but I'm going to mark them in green. Okay, So those are my two beta carbons, right? And if I'm looking at if I'm looking at the hydrogens that are present there, I have a hydrogen in the back here, and I have a hydrogen, one in the back on this side, for this one, and I have another hydrogen in the front on this side. Now, which side would this OH prefer to take a hydrogen from? Which way is going to be preferred? Which side is going to be preferred that that hydrogen gets ripped off of? The left side or the right side? What do you think? The right side, the one with the two hydrogens? No. Why would it not be? Why would it not be the right side that's preferred? Yeah. So the lower energy product is going to be the more highly substituted alkene. That's going to be the one that's connected to more carbon. And so you're always going to want to take the hydrogen away from the more highly substituted side if it's not bulky base. If it's not a bulky base. If it's a bulky base, it's not going to be able to fit in there to grab that. It's just going to take what it can get. So that's why you sometimes have to do the less highly substituted side. Now, the more highly substituted side is called ZSEF elimination. Okay, this is the ZSEF product, and you should be familiar with this term, ZSEF. Okay. That means that the preferred product is going to be the one from the more highly substituted side. The alternative would be a Hoffman elimination, Hoffman, Hoffman elimination. That's when you have a big bulky base that will take from the less highly substituted side. Okay. So another way to think of ZSEF elimination is the poor get poorer. So there's Markovnikov and ZSEF go hand in hand. Markovnikov says the rich get richer, and ZSEF says the poor get poorer. Now, what do I mean by the poor get poorer? I mean that the beta carbon that is poor in hydrogen gets its hydrogen taken away. So the poor get poorer. Does that make sense? An easy way to remember ZSEF elimination. Rich get richer, poor get poorer. Okay, so can I ripple off the hydrogen that's on the left side right now? As is, in its current position? No. Why? It's not opposite to the chlorine. See, the chlorine is dashed, and the hydrogen is dashed. So these are on the same side. Now, you could draw a Newman projection. You could do the whole like visual eye thing. Like, ooh, I got my eye. And the eye is sighting down this bond. And I'm looking at it. Blah, 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 et cetera, et cetera. But that takes a lot of extra work, right? And on the exam, you're not going to have time to do that, I don't think. So if you're going to want to solve a problem like this, just remember, you have to be on opposite sides. The hydrogen that gets ripped off has to be wedged if the leaving group is dashed. So how can I do this? I just rotate the three groups. So I am going to rotate these three groups. So this CH3 is going to come here. Okay? This hydrogen is going to come here. And the ethyl group is going to come here. What's that going to look like? That's going to look weird, isn't it? Well, yes, it is. But that's okay. I'm going to redraw it and show you what it looks like. Okay. So the hydrogen is now coming down here in the plane of the page. And of course, I still have my 1, 2, 3, 4, 5, 6. Okay. And I still have, okay, and then I have this CH3 is now going to be in the back. Actually, I don't like this. I apologize. Let me go ahead and modify this just slightly. I want to pull the hydrogen out in the front, so I should have rotated those the other way. So I'm going to rotate it this way. This is going to go here. This methyl group is going to go here. And then the ethyl group is going to go in the back where the hydrogen is. And so that's going to look like this when I draw it. So methyl group goes down. 1, 2, 3, 4, 5. So now I have a 6 carbon chain in that direction. Cl is still here. But now that ethyl group is now sitting in the back where the hydrogen used to be. Here. So I got a 2 carbon group there. And I have a wedge hydrogen. And then, of course, I still have the other 2 hydrogens on the other side. Now, here's the thing. If I'm looking at this, I know that there's also, of course, a wedge hydrogen here. It's not going to be super important, but I'll just go ahead and put it down here. Now, here's the thing. I have to recognize, the reason I'm putting it down there, though, there is a purpose. There's a reason I'm doing this, and it's to emphasize the local positioning of the different groups. Because when I rip off this hydrogen here, when in fact, rather when the OH minus comes and rips it off, so here's your OH minus. And I'm showing mechanistic steps here because mechanisms are really helpful for understanding these things. So the hydrogen gets ripped off by the OH. These electrons are going to go here, and then this chlorine is going to go away. So in essence, I'm going to get rid of this and get rid of this, and then the rest is going to be my product. So what's that going to look like? It's going to look like this. If I tilt this, if I rotate this thing a little bit this way to make it a little bit flat, what I'm going to do is I'm going to see I have my carbon double bonded to my other carbon, and just for the purposes of clarity, I'm going to go actually label the number of carbons here so you can see what I'm talking about. Here's carbon number 1, here's 2, this is 3, 4, 5, 6, and 7. Okay? So, and this carbon here, down here, I'm just going to call A. I'll actually put a little red dot at the next to it. Okay. So when I'm looking at my product here, relative up position, or rather, the carbons 2 and 1, I'm going to put up here. Okay. And on the bottom, I'm going to have carbon A. So here's carbon 2, here's carbon 1, and here's carbon A. On the other side, what's on the same side as carbons 2 and 1? Carbons 5, 6, and 7. So this will be carbon 4. And 5, 6, 7 are going to be here. And on the bottom, I'm going to have an H. So this is going to be 3, 4, 5, 6, 7. So this would be your major product. This is going to be the most stable product, the major product of this reaction. I know that took a little while to get here, but I wanted to explain in detail all the parts that you need to be thinking about, because unfortunately, in organic chemistry, everything kind of builds off the previous thing, and there's a lot to keep in mind with a reaction like this, and admittedly, in a final exam, you're going to have to go through these steps pretty quickly, but I wanted to explain each of those steps so that it was totally clear how I'm getting what I'm getting. Any questions on this so far? It all makes sense? Okay. Then what about the minor products? So here's the thing. If I look at the beta carbon, the other beta carbon, which is actually carbon number 5, the other beta carbon has both a wedge and a dash hydrogen, which means that you can get both cis and trans isomers here. Cis and trans isomers here. So if I went, so this here, this will be your major product. This is your major product. But you're also going to get 2 minor products as well. You get a total of 3 products here, 3 possible elimination products. There's your major. The minor one is going to be essentially between, the double bond is going to be between 4 and 5, because 5 is the other beta carbon, and double bond always forms between the beta and the alpha carbon. Let me emphasize that. Double bond always forms between the beta and the alpha carbon. Okay? Those are the only possibilities. Beta and alpha carbon, those are the only possibilities for an alkene double bond between those types of carbons. Okay, so cis and trans between carbons 4 and 5, or what are at least originally I've labeled as carbons 4 and 5, although that would actually change in the context here. So 1, 2, 3, 4. So this would be 4, 5, 7. 1, 2, 3, 4, 5, 6, 7. So this would be the trans product, except that I have to add my methyl group on carbon number 3. And I actually accidentally flipped this for some reason. I don't know why I chose to do that. Ooh. Let me, I'm going to actually, there is stereochemistry here, so I'm actually going to, I got to make sure that I don't mess this up. Okay. But basically, I can't just write it upside down, because then I would have to change this from a dash to a wedge, or a wedge to a dash. But here's your methyl group. It is wedged. This does have stereochemistry here, and it will continue to have stereochemistry. So you have that one. That's going to be one of your minor ones, and your other one is going to be a cis minor. So it would actually look like this. I'm going to find my cursor. It's a little hard at times. 1, 2, and it would be 3, 4, 5, 4, 5, 6, 7. So you'd have this, and then you'd have, so you'd have the cis and the trans isomer here. So those would be your 3 products, the major, and then these 2 minor products. Okay, what else can I help you with? Oh yes, Aurora, go ahead. I see there's a hand up. What can I help you with?
Hi, can we please go over resonance?
Yes, absolutely. Resonance is one of those areas that is particularly confusing for most students, so I'm glad you brought it up. Let's go ahead and I'm going to drag this over here a little bit. Can you hear my Wisconsin accent? Drag, dragon, bag. That kind of stuff. Okay, so here we go. Let's say you have something like this. This is a good one because actually this is an example problem from a test that Dr. Gilchrist had, and it basically says draw at least 3 resonance structures for the following compound. And this will give me a good opportunity to go through the different principles for guiding resonance. So first principle is this: resonance can only occur between sp2 hybridized atoms, okay? Or st hybridized atoms, but sp hybridized atoms resonance is much less likely to occur, and you rarely see it. But so you have to have either sp2 or st hybridization. How can you check if something is sp or sp2 hybridization? You look at the number of electron domains around an atom, okay? So if I look at that oxygen with the minus charge, actually, let's look at a particular carbon. I'm actually going to put a little carbon. I'm going to mark this little carbon here in blue. And just for the sake of clarity, I actually am going to show the bonds to hydrogen that are present in this particular molecule, because I think it'll be helpful. Ah, there we go. And I'm going to copy it. There we go. All right. So, and I'm looking at this, that blue carbon that I just labeled. How many electron domains are around that thing? How many? Say a lot of 0. Electron domains are regions of electron density. Now, a region of electron density can either be a single bond, a double bond, a triple bond, or a lone pair. There's 3 electron domains. Yeah, this should be automatic for you guys. All right. Because it is 3 electron domains, that means it'll hybridize 3 orbitals, which means it's going to be what? sp2. If it was 4 electron domains, it'd typically be sp3. All right. Now, there's 2 ways something can be sp2. One is by having 3 electron domains around it. Another is by having 4 electron domains if at least one of those electron domains is a lone pair and it's next to an sp2 hybridized atom. So let's look at this oxygen here, the one with the negative charge. How many electron domains are around that? With the oxygen. 4. There's 3 lone pairs and one single bond. Now, even though it technically has 4 electron domains, if an atom like that is next to an sp2 hybridized carbon or any sp2 hybridized atom, it will also be sp2 hybridized if it has a lone pair. So that oxygen has lone pairs, right? And is it next to an sp2 hybridized atom? Yes, it is. So because that carbon here, where's the little pointer? I want a pointer. Here we go. Yeah. Because that here is sp2 hybridized, that means that this is also sp2 hybridized. So these are all sp2 hybridized, and you can resonate between them. Now, when trying to figure out all the different possible resonance structures that you can have, you want to move one step at a time. What that means is that whenever you're showing resonance, you always want to move electrons from areas of more negative concentration to areas of less negative concentration. So more negative, obviously the negative charge on the oxygen, that's where I'm going to focus my attention. I'm not going to worry about the electrons that are part of pi bonds in the middle of the ring. So because this has a high concentration of electrons, I'm going to move it here, and I'm only going to move it one step. I'm only going to move it from either atom to bond or bond to atom, but never from atom to atom or bond to bond. In other words, I'm not going to take something like this pi bond here and then suddenly move it and make it a pi bond over there. I'm not going to do that. So atom to bond, bond to atom. So in this case, these electrons are going to form a pi bond between that oxygen and that carbon, and then that's going to actually put 5 or 10 electrons around that carbon, so something's going to have to break. This pi bond will break, and it will put those electrons right here on that atom right there. So that's going to give you the following resonance structure. This will no longer have 3 lone pairs. Instead, it will have that. And this will no longer have a double bond. Instead, it will have a lone pair on that carbon right there. And it will also have a negative charge. Okay. So, next, I'm going to move those negative electrons, right? Where am I going to move them? Yep, I'm going to move them over to the right. So this is going to go to atom to bond, form a double bond, and that's going to break this pi bond, which is going to go from bond to atom. And I'm going to get yet another resonance structure. Clean this up. It's going to go away. No longer have that. Instead, I will have this, and I'll no longer have this. Instead, I will have a lone pair of electrons on this carbon over here, along with a negative charge on it. Whoa, there we go. All right. So now I have another resonance structure. And then I will basically continue to do that until I've gone completely around the ring. I'll do another resonance structure where I will take the negatively charged electrons here. Change my color to green. Atom to bond, bond to atom. And if I do that, that's going to give me this. Okay. Bye-bye lone pair, bye-bye negative charge. Hello double bond. Bye-bye this double bond. Hello negative charge and lone pair. And technically speaking, one could say, well, you can also then move these electrons. You can move these electrons back here. Let's see. And that's going to kick these electrons back up to the oxygen. which is basically going to give you your original Lewis structure, original resonance structure. Does that make sense?
Yes, thank you.
You're welcome. I hope that helped. Resonance, it can be tricky, but just keep in mind that the rules for resonance are that, one, you'll resonate between sp2 hybridized or sp hybridized atoms only. Two, you'll tend to go from more negative towards less negative. You'll move electrons from more negative areas to less negative areas. And three, just do it one step at a time. Atom to bond, bond to atom. Now, the most stable resonance structure, how do we figure out what the most stable resonance structure is? Anybody know? What's one of the criteria?
The one with the most full octets.
Well, let's say they all have. You're correct. You want them to have full octets. So you do not want them to be electron deficient. Okay. Let's say in all the resonance structures, they have the same number of octets, or as close to it as possible. What are some other things that make something a better resonance structure? A negative charge on the most electronegative atom, which means in this case, which is your best resonance structure? The first one. This one is the best because it has the negative charge on oxygen, which is the most electronegative atom. Does that mean there's not actually a negative charge on any of these other carbons? There's still a little bit. Actually, the truth is there's not really a full negative charge on any of them, including the oxygen. But there's going to be a partial negative charge on each of these, but the biggest partial negative is going to be on oxygen. With resonance structures, a good analogy is like paint. If each one of these resonance structures is a different color of paint, let's say this one's red, this one's yellow, etc. If I mix the actual quote-unquote molecule is orange, it's not red or yellow, it doesn't bounce back and forth between red and yellow. It actually is kind of a blend or a mix of all of them together, so to speak. I know that's an imperfect analogy, but I hope that kind of makes some sense. But the most important resonance structures, the ones that are most stable, those are going to be the major contributors. Those are going to be the ones that have the most influence on where these partial negatives and such are. Another factor, other than most electronegative element having the negative formal charge, is minimizing formal charges. So the best resonance structure is going to have formal charges as close to zero as possible in as many atoms as possible. So that's another factor. That's why we don't get something like this. This, technically speaking, would be an actual, shall we say, resonance structure, at least a possible resonance structure, but it's astronomically unlikely because it would be so unstable. So I'm going to show you an example of a resonance structure that would be very unlikely for this molecule. So you could have a situation where you have this oxygen and it has a negative charge here, but then this, and there's of course hydrogens all around, but this one, the electrons from the pi bond move to this one, so there's a negative charge here and a positive charge here. So technically speaking, could that happen? Well, yeah, theoretically, possibly. But the likelihood of that happening are so remote that this is what would be considered not a significant contributor to resonance. Does that make sense? It might have some tiny, tiny, tiny effect, but the effect is going to be so small as to be insignificant and not able to be measured. Okay, does that make sense? Cool. All right. What else can I help you with? Oh, anyone wants to take a picture of the screen, you can. Yes? Radical bromination? No, I don't want to do that. No, I was kidding. Okay, I can do that. All right, let's do it. Radical bromination. So, for these free radical reactions, you have to keep in mind that there's 3 different types of steps to the mechanism: initiation, propagation, and termination. We'll go through each one of those types of examples. I'll do an example here. Let's make it fat. I want to make it fat. Here we go. Here's their initiation. I'm gonna color code it too, just because I'm nerdy like that. The initiation step always involves going from 0 radicals to 2 radicals. So, in the case of free radical bromination, there is one initiation step. And that initiation step is bromine gets hit with light. Now, actually I'm going to do this because this is more fun. Boop, 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 and it's easier. Here's my lone pairs. Okay. So bromine gets hit with light, and then when it gets hit with light, it splits this bond homolytically. This is referred to as homolytic cleavage, which means it splits it evenly. Half of the bond, or basically 1 electron, goes to the 1 bromine atom, and half goes to the other. That's why you have these half arrows, or what's sometimes called fishhook arrows. So this splits homolytically, and then you get 2 bromine radicals. So, radicals. So radicals are very unstable, so this, once they form, you start reacting immediately. And that leads us to our second type of reactions, the propagation reaction. Propagation. And that's when you go reaction, you can tell it's a propagation reaction because it goes from 1 radical to having the same 1 radical. The radical just switches from one part to a different, from one molecule to a different molecule. So let's do the reaction in this case. Yes. Oh! How did that happen? Okay. Is that better? No, it's not. Okay. Oh, actually, you know what? I'll just do this. Okay, no, I can't do that. I'll do this for now. Then I'll do the other thing. You can see it now, right? Kind of. And I will minimize that. There we go. You can see our radicals. Okay, next, propagation. Okay. Let's say that this reacts with something like this. A alkene that has 2-methylbutane. Okay. So now, here's the thing. Bromine reactions are highly selective. With chlorines, you're actually going to get a mixture of products, but bromines are preferred because they're highly selective. Bromines will always, free radical bromination will always occur at what position? Least substituted or most substituted? Oh, you should know this. What did you say? Actually, the most substituted. That's okay. That's okay. So that's why we're reviewing now. But yes, the most highly substituted position, which means of all these carbons, the one that the bromine is going to want to add to is this one. This is the favorite spot, most highly substituted. But it's not going to add right away because it can't. Because right now, this carbon has a hydrogen right here and has 4 bonds. It's not wanting anything. However, bromine radical is like, you took my spot, I'll make you pay. So, make him pay, bromine radical. Make him pay. And pay he will. Bromine will abstract him. You get fish hook arrow, whoop. And then this one splits also with a fish hook arrow. And that causes 1 electron to go to the position right there. And the reason why it picks out the tertiary is because tertiary radicals are the most stable radicals compared to like secondary and primary. So you're going to want the most highly substituted radical, which is a tertiary radical. Let's do it. So that's going to give you okay. And then let's see. This now has a radical right here. And you also have HBr. So plus HBr. Oh, whoa, what happened? What on earth did I do? Oh, there it is. Okay, HBr. There you go. So that's one. You go from having 1 radical on the bromine to 1 radical on the alkyl group. Then you can go ahead and do the same thing. Now this radical is still very unstable. It's going to react with what it most wants to react with. Well, it turns out that bromine is really attractive to this. The bromine is really attractive to this. Now, if I have a bromine, Br, and it's fully intact, because keep in mind, when you get the split in the initiation step, that doesn't affect but a very small fraction of the bromine molecules. There's still a lot of unreacted bromine molecules out there. And so these are going to be targets for these radicals that form. And that's going to cause this one to split the bromine and form another bromine radical. And then that can cause, then you can get a repeat of the first reaction. So bromine radical forms, then alkyl radical forms, then bromine radical forms, alkyl radical forms, and you get the chain reaction. It keeps cycling through this, and the reaction happens fast because these radicals are really, really unstable and very reactive. So then, let's see. Oh, whoops. Switch this to this. So that's going to give you one of the final products here, that what is most likely the desired final product, which is this 2-bromo, 2-methyl butane. And then, of course, you also get a bromine radical, like I mentioned. Now, to answer the question that everybody's dying to ask, and I know you're all thinking about, could that bromine radical that you started with just react with bromine instead? In other words, a bromine radical with the Br2? Yes, but why don't we care about that reaction? Why don't we care about a reaction of this with another Br2? Because it wouldn't change anything, right? You'd go from one radical and one bromine molecule to one radical and one bromine molecule, and it's like, who cares, right? So that doesn't move anything forward. So in this case then, after you have these two propagation steps, we'll have a series of termination steps. So termination. Yeah, the terminator. Termination steps. Okay, and termination steps go from having 2 radicals to 0. I'll actually spell it. 0. With an exclamation point. Just for fun. Okay, so 2 radicals to 0. So there are several possible termination steps. You could have a bromine radical react with another bromine radical, and forgive my sloppy dotting. And if these two guys get together, this is just going to be a reverse. This is just going to be a reverse of the initiation step. But it is one of the termination steps. So it can stop like that. Br2. My drawing really is atrocious. I do ask your pardon. There we go. Now, the other possibility is you could have one of these guys. Ooh, I just found an easy way to make myself have to do less drawing. Copy, paste. I could have one of these guys react with copy, paste, one of these guys. And if I do that, then I get the same final product that I was interested in the beginning, which is 2-methyl 2-bromo. So I get one of these bad boys. Copy, paste. So that would be the second termination step. Third termination step would be is if I had one of these alkyl radicals. Copy, paste, paste. Could have one of these bad boys. And fit these two guys together. And if those stick together, it gives me a really weird looking molecule. I don't actually really feel like I want to draw it, but I think I have to. Yeah. So it ends up giving you something that looks like this. Because the longest carbon chain is going to actually be 6. And then you're going to have 2 methyl groups coming off of this one, and 2 methyl groups coming off of this one, basically. So those would be your termination products. So you got your side product. The bromine's not a big deal because that was what we originally started with. And that'll keep on reacting until you get to the very end. But the one of these that will not react and that will kind of accumulate as a unwanted side product is this one right here. Because it doesn't have any tertiary hydrogen, so it won't continue to react. And it also, once it forms, it's really kind of out of the running for reactivity. So that's how to explain these free radical bromination reactions. Initiation, propagation, termination. Does that make sense? Any questions? What's next? What else can I help you with? Yeah. Oh, go ahead. Oh, yes. Okay, so probably one of the most important resources that I would want to direct your attention to is the substitution versus elimination flowchart. And I'm actually going to, for those of you watching online, I'm actually going to switch sharing. Here we go. Substitution versus elimination flowchart. It's probably one of the hardest things you've dealt with all semester is trying to discern between SN1, SN2, E1, E2, and all the different possible iterations of that, right? There's a series of questions that you can ask yourself that will really give you some good clarity as to what you're looking for, what you're going to expect with a particular set of reactants. The first thing you want to look to is answering the question, is there a good leaving group? Or can you make it a good leaving group? I'm going to actually zoom in a little bit. Zoom in. Oh. Zoom in, darn you. Oh, here it is. There we go. So, is there a good leaving group or can you make it a good leaving group? If there's no good leaving group on a reactant, it's not going to react. So there's going to be no reaction. If there is a good leaving group, you have to ask yourself, where is the leaving group located? Is it on a primary carbon? Is it on a secondary carbon? Or is it on a tertiary carbon? Primary, secondary, or tertiary. Now remember, primary carbon is one that's attached to only one other carbon. This is a little hard to see because of the yellow, but primary carbon. Secondary is attached to 2 other carbons. Tertiary is attached to the carbon that's attached to the leaving group is attached to 3 other carbons. From there, you have to ask yourself, is there a strong base present? Okay? So if the leaving group is attached to a primary carbon and there is a strong base present, you have to ask yourself, is the base a good nucleophile, like OH minus or CH3O minus? If not, it's E2 only. So a base that would not be a good nucleophile would be something like this: NaH, DBU, or DBN. Those would all be pretty terrible nucleophiles, and therefore they're strong bases that are terrible nucleophiles. So that would give you E2 only. Okay. So if it's a strong base that's not a good nucleophile, E2 only for primary carbon. If it is a good nucleophile but it's sterically hindered, then it will give you E2 only, But if it's not sterically hindered, you'll get the majority SN2 with a little bit of E2. So an example of a case where it would not be sterically hindered, but it's a good nucleophile, would be something like a CH3, CH2, OH minus, or O minus. Sometimes they'll put a potassium on the end, CH3, CH2OK, or CH3, CH2ONA. But that would be an example of, it's a good nucleophile, it's not particularly sterically hindered, so the major product is going to be SN2 with maybe just a little bit of E2 minor product. Now, of course, if there's no strong base present, the only possibility is substitution. And so therefore SN2 only. But if heat is added, and if it's not a good nucleophile, and there's no heat added, there's no reaction. But there's not a good nucleophile and there is heat added, you can get a possible E2 elimination. This is one possibility that the book does not really talk about. So specifically where this would happen would be is if you have acid catalyzed dehydration of a primary alcohol. That will occur if you add heat. Acid catalyzed dehydration of a primary alcohol will occur if you have heat. But without heat, it will not occur. Because you're basically trying to force an E2 elimination without a strong base. And that's hard to do. So you need some energy. Now, secondary, this one's a little more straightforward. Well, okay, I lied. It's not straightforward. It's complicated. But strong base present? Yes. Is the base a good nucleophile? No, E2. No, whenever the base is not a good nucleophile, and it's a strong base, it's going to be E2. Is the base a good nucleophile? Yes. If it's sterically hindered, yes, once again, E2 only. If it's not sterically hindered, with a secondary, because the secondary is already somewhat sterically hindered, even if the base is not sterically hindered, if it's a strong base, E2 will be the major product. SN2 will still happen, but it will be a minor product. And then once again, good nucleophile, yes. If it's not a strong base and a good nucleophile, SN2 only. If it's a weak base and weak nucleophile, so not a strong base, not a good nucleophile, the question is heat added? If yes, E1 elimination will dominate. If no, SN1 nucleophilic substitution will dominate. And you can kind of go over this on your own, but the nice thing about this is you really want to be familiar with this. You really want to be familiar with these questions. This is not something necessarily to memorize per se, but it's something to kind of like help you to recognize what sort of questions you should be asking yourself to check and see if this is something that would undergo elimination or substitution. Does that make sense? A consistent set of questions you can ask yourself to determine. No. There is a list of good nucleophiles and strong bases here. You do want to be familiar with those. You do also want to be familiar with good leaving groups. So this definitely will help. But unless your professor gives you a note card to write all sorts of note stuff on it, it's not going to be super helpful unless you have most of this committed to your mind. One is particularly important strategy here is to ask yourself why. Why would a strong base present favor E2 elimination? Because a strong base is very reactive and therefore it's impatient. It'll grab whatever it can get, even if it's a good nucleophile. And if it's not a good nucleophile, even more so. All right. What other questions do you have? Is there anything else I can help you with?
Can you go over how to use chirality centers to determine if something is a diastereomer or an enantiomer?
Yeah. So can I go, the question was, can I use, go over how to use chirality centers to determine if something is an enantiomer or diastereomer?
Yeah, like the RNS configuration.
Yes. So to that, let me go ahead and I'm going to share. I'm going to switch my sharing. Cancel this. Okay. So I'm going to go to a different section. But there is a useful kind of flow chart here you can use as well. So to determine like the different levels of organization or the different types of isomers that you have, this is a good flow chart for guiding your responses. First of all, does each molecule have the same number of atoms of each type? Same number of atoms of each type, okay? If the answer is no, if the answer is yes, then you have to ask yourself another question. If the answer is no, that means they're not any type of isomer. Okay. Next. So the next question, if it's yes, then you have to ask, do the atoms in the two molecules have the same connectivity? Connectivity means that the same atoms are connected to the same other atoms. So, do the atoms have the same connectivity? If the answer is yes, then we have to ask another question. If the answer is no, then they would be structural isomers or constitutional isomers. Those are two different ways of saying the same thing. Structural isomers. So if I said yes, then you have to ask yourself another question. What is that question? They have the same connectivity. The question is, are they superimposable? Are the two molecules superimposable with each other? So then, if the answer is yes, that means they're not isomers at all. They're the same compound. If the answer is no, okay. So, oops, wrong one. There it is. Same compound, and they're not isomers. But if no, then you have to ask, are they mirror images? Although actually, technically speaking, forgive me, I think actually I should ask if they're mirror images first. So, yeah. Okay. Are they mirror images? Yes or no? If they're not mirror images, that means that they would actually be diastereomers. Now, here's the thing. Diastereomers can either be one of two things. It can either be cis-trans isomers or alkene EZ isomers, or the RS isomers with two or more stereo centers or chiral centers that are not opposite configurations of one another. So that's what you were talking about in terms of, try that. So there's diastereomers, there'd be cis-trans isomers, EZ isomers, or RS isomers with two or more chiral centers that are not opposite configurations of one another. And I will explain further what I mean by that. Let's go ahead and this, let me change color thing. Okay, there we go. And then we'll move this over. Now, if they're not mirror images, what do I do? Here. If they are mirror images, you have to ask, are they superimposable? Oh, undo. And that is when and if the answer is no, then they are enantiomers. Because they're non-superimposable mirror images, so they would be enantiomers. If the answer was yes, then they're not isomers at all, they're the same compound. Now let's zoom out and get a better look at this. So, does each molecule have the same number of atoms of each type? If no, they're not isomers. If yes, do they have the same connectivity? If they don't have the same connectivity, they're structural or constitutional isomers. If they do have the same connectivity, you ask if they're mirror images. If they are not mirror images, they are diastereomers. If they are, you have to check and see if they're superimposable. If they are superimposable, that means they're the same compound, or a meso compound, which is basically the same compound. That or they are enantiomers, if it is not superimposable with its mirror image. So one easy way to tell, if you have a compound, let's say that looks something like, gosh, I wish I had some ready examples, but I can make one up. Zoom in. Zoom in one more time. Let's come and take a look at something like this. Okay, let's say you had something like this. Right, this one is wedge, and this one's wedge. Here's a Cl, and here's the methyl group. Okay. Now, first of all, how many chiral centers do you have here in this compound? No. It looks like there's two, but what's the problem with one of them? Remember, to be chiral, you have to be bonded to 4 different groups, right? If you look closely at this CH3 is the same as this CH3. They're both CH3s, so it's not chiral. Be careful, sometimes professors like to throw stuff like that at you. So in this case, there would only be one chiral center. Now, what would the designation of that chlorine be? Would that be an R or would that be an S, stereocenter? Yeah, because this chlorine's going to be highest priority. That's going to be 1. This would be 2. And then this would be 3. Of course, the hydrogen's in the back. So this would be R. So then I'm going to go ahead and label this R. R stereocenter. Now let's say this was instead of a methyl group. Say this is an OH. What would this chirality of, what would the designation of the other chiral center be? Yeah, because it would be, the OH would be the first, and then the side with the chlorine would be the second, and then the other third. So actually, this would be R as well. It'd be R as well, because this would be number 1, 1, 2, 3. And then the hydrogen's in the back, so it ends up rotating like this, right? Clockwise, and clockwise would be R if hydrogen is in the back, or the lowest priority group is in the back. So I'll remove those designations. I'll just write the designation. This is an RR. Now, if I was to take a similar molecule, a stereoisomer of this one, if I did this, what would be the relationship between these two? Well, we can check the surest way to tell would be to go ahead and check the designation of each of the chiral centers. What would be the designation of the chiral center of the chlorine that's dashed? What would that be? Yeah, it would be an S, right? What would be the designation of the OH? R. So are these configurations opposite of one another? No, right? RR and SR would not be opposite of one another. So what are these? Are these enantiomers or diastereomers? Diastereomers. Now the enantiomer of this would look like this. The enantiomer would look like this. Or at least one of the ways you could show the enantiomer would be to look at it like this. Because in this case, both the chiral center here and the chiral center here would both be S. So SS, RR, those would be opposite configurations. It means basically you flip the configuration from R to S on each of the chiral centers. If that is the case, then you have an enantiomer. If it's not the case, then you don't have an enantiomer. If they're going to be enantiomers, they have to have opposite configurations. Does that answer your question?
Yes, it does. Thank you.
You're welcome. Okay, and somebody else had a question. Oh, okay, okay. So there's two different questions. They're both reaction questions. So I'm going to go ahead and switch to a new, new whiteboard. Give myself a little bit more room, make it a little bit cleaner. Okay, so the first reaction is an alkyne reaction. It looks like this. Okay, so if this were treated with ozone, followed by water, ozonolysis followed by water, what would the products be? So the key thing is when you're cutting these alkyne triple bonds and you're predicting the products, what you have to remember, or when you're using ozonolysis almost invariably always splits, cuts, severs, whatever triple bond or double bond might be present. So this triple bond here is actually going to get cut right down the middle, and it's going to give you two different molecules. Now note the number of carbons on each side here. On this side you have 2 carbons, and on this side you have 1, 2, 3, 4, 5. And it's really helpful sometimes to number or label these as well, because it's not always easy to keep track of how many carbons are on each side of the 2 new molecules you're creating. But what ozonolysis is going to do, it's actually going to turn these 3 bonds to carbon, to each other, into 3 bonds to oxygen. And in fact, it's going to turn it into a carboxylic acid group. So what's that going to look like? Well, I'm going to have a 2-carbon carboxylic acid. So 2 carbon, and then 2 bonds to oxygen here, 1 bond to oxygen here, OH. And then I'm going to have the same thing on the other side. This, those carbons there, and then this carbon's going to have a 2 bonds to oxygen down here, 1 bond to oxygen up here, OH. So 2 carboxylic acids. So ozonolysis is going to split alkynes into carboxylic acids. It'll split alkenes into aldehydes and ketones. Note the key distinction there. If this was an alkene, it would split it to aldehydes and ketones. And I'll even show an example of what that looks like, because you very well might see a reaction like that as well. And you're going to want to be able to distinguish between the two. So let's say you have something like this. Well, if you ozonolysis this, and this is typically it's O3 followed by like DMS, dimethyl sulfide, or something like that. This is going to, so the reagents are slightly different, but it's still an ozonolysis reaction. It still does the same type of thing. It splits the double bond down the middle. This particular one, actually, let's change it up just a little bit. I'm going to put this right here. And once again, I'm going to label all of my carbons to keep track of them. Keep track of them. There we go. So, with this particular one, I have a 3-carbon group on the left-hand side. Instead of having that 2 bonds to another carbon, it's going to be 2 bonds to an oxygen. I get this. In other words, if I'm looking at this, this is 1, 2, 3. That's going to be these 3 over here. 1, 2, 3. Then I also have the other one. Instead of 2 bonds to a carbon right there, I'm just going to be 2 bonds to an oxygen. And this is actually going to be an aldehyde. I'll actually draw the little hydrogen here. It's not shown in the original compound because you don't usually draw the hydrogens in a carbon-hydrogen compound. But with an aldehyde, you usually do draw that hydrogen. Essentially, you have an aldehyde and a ketone that form in the case where you're splitting aldehydes and ketones form when you ozonolysis an alkene. So keep note of that difference, ozonolysis of alkynes versus ozonolysis of alkenes. Also, one other important thing to note, were you to apply ozonolysis of an alkyne that was terminal, is it okay if I move down? If this was terminal, here's what it would look like. So what do I mean by terminal? I mean you have something like this. I'll keep it simple. Propyne. So if I split this down the middle, I have 1 carbon on one side, and I have 2 carbons on the other. And so an ozonolysis of this type, copy, paste, is going to give you, on the left-hand side, once again, you're going to get that 2-carbon carboxylic acid. But what's interesting here is on the right side, you're going to get, because there's only 1 carbon there, you actually get carbon dioxide, CO2. Keep that in mind with the alkynes. If you cleave a terminal alkyne, one of the products you're going to get is CO2 because that carbon that's all by itself, it's going to maximize the number of carbon-oxygen bonds. And it ends up basically giving you a carbon double bond on one side and a carbon-oxygen double bond on the other. Well, that's CO2. That's carbon dioxide. Okay. So, next. The other one was propose a synthesis of the following transformation. Is it okay if I scroll down? So I don't know if you've done much with synthesis, but these are kind of fun problems. Of course, you might also hate them, but I say fun because they're challenging, but, you know, I'm weird. So how would you synthesize this from this? Well, here's the thing. Anytime you're starting out with an alkane, there's really nothing you can do with an alkane except one reaction. There's only one reaction you can do with an alkane. What would that reaction be? What? Nope. Only one reaction that you can do with an alkane. I'll give you a hint. It's a recently learned reaction. What'd you say? You can't add anything to it unless you use what type of addition? Free radical bromination or free radical chlorination. There's only one type of reaction you can do with an alkane. One and one only. This is the only type of reaction that will really work in an alkane. That allow you to add some things and actually put some functional groups on this thing. The only thing that you can really do with an alkane, bromination. Bromination is preferable. You can also use chlorination, but bromination actually gives you a more certain product. The bromination will do the more highly substituted. So what are the reagents for bromination? That would be Br2 and There's actually two possibilities. What do you need for a free radical reaction? Anybody? Heat, yeah, but what light? Light or peroxide. And light is usually indicated with this like HV. H Planck's constant. That V is actually the Greek letter nu. It's for frequency. So yeah, that's going to give you the more highly substituted alkyl bromide. Okay, now that I have this alkyl bromide, what could I do? Well, bromine's a good leaving group by itself. What'd you say? What's that called? Rip off a hydrogen to make a double bond. What's that type of reaction called? E2 elimination. And you can use pretty much any base you want, but you want to use a base that will make sure that it turns it into a double bond. Now, here's the thing. If you use like NaH, something that is a poor nucleophile but a good base, you will get this, but which is basically what this is, right? The only problem is, unfortunately, you'll also get this. So, because of that, this may not, I mean, you could say, technically speaking, the trans product is the major product. Maybe you could put that. The question says propose a synthesis. It's like, yes, you could. But the truth is, this isn't necessarily the best synthesis because you still have to separate the products. And that's not always easy to do, especially with stereoisomeric products like this. So if you really wanted to get 100% trans alkyne, or alkene rather, you do the next step here. You do a bromination reaction, Br2, with CCl4. And why would you do that? Why would you do that? What can I do with this? What can I do when I have two bromines on something? What'd you say? You can make an alkyne, right? Yeah, and you can make an alkyne with excess NaNH3. So especially with this, I can make an alkyne. So I'll do 1 excess NaNH3. Or NaNH2 rather, sorry, NaNH2. And after you've ripped both those hydrogens away, got the triple bond, then you can follow it up with a little water to neutralize the excess base. Okay. And that's going to give you this bad boy right here. Now, what could I do with this guy to get 100% transalkene? What'd you say? Na and NH3. Sodium and ammonia reduction. So if I put sodium metal, Na, and ammonia, that sodium ammonia reduction would give us a transalkene. 100% yield. No need to separate. No waste. Okay. Any other questions? I'm sorry? Show me which one. That one?
Yeah, I think, yeah,
Okay, so this is a free radical bromination using allylic bromination with NBS. So NBS is an interesting, it's an interesting molecule because it doesn't give you bromination in the way that you would expect. So yeah, okay. So here's the deal. You've already learned about several different types of bromination. One is like the free radical bromination of an alkane. That's Br2 with HV. And that gives you this, right? Another is bromination of an alkene using HBr. And that gives you something like this, Br here. And actually, just for the sake of comparison, I'm actually going to change this to this. This gives you the bromine in the more highly substituted spot. I could also get something like this. I could have the same compound react with HBr, but then use peroxide, which is ROOR. And if I have peroxides like that, that's going to give me the bromine in the less highly substituted position, as to the less highly substituted carbon. But notice that in these other reactions with an alkene, the alkene goes away, right? But with NBS, you get something entirely different. NBS, you get something entirely different. Were you to react this same compound with NBS, what happens is it brominates the allylic position. The allylic position is the position next to the double bond, not the double bond itself. So the double bond itself remains. So what NBS does, it actually forms a radical on the alkyl group in this position here. But this radical delocalizes because you can actually have resonance here. Essentially, what happens is the pi bond here can split, and this radical can go together to form a new pi bond there, and that can put the radical on the other one, the other carbon, which can give you this. Now, either one of these can then react with the bromine, because NBS actually does produce a bromine, Br2, in the course of this reaction. It's an interesting mechanism, which you'll probably not be responsible for, but it's useful to keep in mind that it does actually produce Br2, which means that each one of these radicals can then form, or can then react with the bromine to form the new compound. So if this radical reacts with the bromine, I get bromine on this position. If this radical reacts with bromine, I get bromine on this position. Sorry, and I know I didn't draw this terribly well. The carb, I'm going to draw a little carbon here. This is a carbon, carbon. My drawings are terrible right now. And then this is also, of course, a carbon that has a radical electron on it. Does that make sense? So NBS puts a radical in an allylic position. That allylic position then can resonate between two different positions, and then you'll get a bromine adding to either one of those. Now, in the case of the particular problem that you were asking me about, there was this thing. It looked like this. Okay, it was a dot, 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 and then this. So in this case, what you would see is that the initial reaction with NBS is going to put a bromine radical here. That bromine radical then can delocalize. It can there can be resonance, and you can get the bromine radical on this outer position with a double bond shifted here, because what happens is you get the little fishhook arrow in this spot, and this has to go here. And then if one of these reacts with the available bromine, then you get the bromine here. And then if the other one reacts with the available bromine, you get the bromine adding here. And that's why you get those two. That's why you get those two things. And there you go. That's all that there is to it. So the initiation step for the NBS is actually, the initiation step is I actually can't really exactly remember what N-bromosuccinimide looks like. I think it looks like this. It's like, oh, actually, no, it's like this. It's a weird looking molecule. Here it is. You got double bond O's out here. You got a single bond right here. Double bond O's out here. And then you have a nitrogen here. And you got the bromine here. N-bromosuccinimide. And this bond right there, that bond between nitrogen and bromine, is particularly susceptible to splitting. So the initiation step here is the splitting of the NBR bond to form a bromine radical and a succinimide radical. And basically, what happens then is the bromine radical will react with other N-bromosuccinimides to produce Br2. And then the N-succinimide radical will react with, because this nitrogen actually already has a lone pair on it, this nitrogen radical will react with the original alkene in the allylic position to pull off a hydrogen. So essentially, the first propagation step for this particular reaction here is going to be this guy, dot, dot, oh, whoops, I lied. It's gonna be, and you have this hydrogen here, and then you have this guy here, which I don't want to redraw, so I'm going to actually copy it. Flip. Yeah, that's what I'm talking about. Make myself some happy electrons. There we go. And force you to listen to my terrible singing. Okay, here we go. So, this is going to come fish hook arrow, fish hook arrow, fish hook arrow. That's propagation step number 1, which is going to give you that. And it also gives you the hydrogen with the N-bromosuccinimide. And actually, let me just go ahead and that actually doesn't work. Just have to do a little bit of modification. And then put a hydrogen on there. There you go. And then so that, sorry. Now, like I said, the bromine radical reacts with more N-bromosuccinimide form Br2. So the next propagation step, because it says it only wants 2 of the propagation steps, the next propagation step would either be this or its resonance contributor going to form this reacting with a Br2. And then at this point, you should be kind of familiar with what's going on here. But that's basically the mechanism for NBS reacting with an alkene. And then react in the allylic position like that. Split. Fish hook. Fish hook. Fish hook. And that gives you another bromine radical, which of course will react with another NBS to form another bromine, which will react with other stuff. Oh, it's an interesting reaction how it works. But yeah, so that's where you get those products. Any questions on that? Does that make sense? Have I satisfied your curiosity? Good deal. Yeah, there's a lot on the Neochem file. There's a lot of concepts, a lot of these reactions. But if you've been studying mechanisms this entire time, really like getting down to the nitty-gritty of how these reactions work step by step, that this is actually going to be a piece of cake for you, I think. If not, memorization's going to be your best friend at this point, because if you haven't learned the mechanisms by now, probably not enough time to learn them. But anyway, I hope this session was helpful for getting you to understand some of these concepts. I'm afraid we're out of time now, but I wish you the very best on your final exam. Of course, we will still be here tonight and tomorrow in the Science Learning Center, so feel free to stop on by and get help with anything you'd like help with. And y'all have a wonderful evening. You're welcome. Thank you for coming.